Well, last time we reviewed how to take a stress state and find the principal stresses and the maximum shear stress. And now we're going to use those to predict failure. And in particular, we'll be looking at ductile materials today and brittle materials next time. So what seems like a logical thing to do once you've found the principal stresses is to try to compare the principal stresses to the strength of the material, in this case the yield strength, and say that's a prediction of failure, that is the maximum principal stress criterion. Now, it doesn't always work very well, and we'll see later on the cases where it doesn't work very well. But again, we present it just because if you calculate the principal stresses and then compare it to the yield strength, then really what you are doing is applying this criterion, whether you realize it or not. Now, so the criterion itself, though, says that when the magnitude of either the principal stresses, and if we order them from sigma 1 to sigma 3, then sigma 1 is always going to be the biggest, sigma 3 will always be the smallest, so in other words, the greatest value of compression if any of these are in compression, then when either of those magnitudes reaches the yield strength, then you have failure. And so the factor of safety then is just the ratio between the yield strength and the principal stress. And so again, if you have compression, need to check both the maximum and minimum values to see which one is greater, or which one is less in this case, which one is critical rather. So as we said, that really doesn't work very well in a lot of cases. One that does work pretty well is the maximum shear stress criterion. And it predicts that when your maximum shear strength reaches the yield strength in shear, then you have failure. Let's think about a tensile test for a moment. If you pull on this bar, the stress in the x direction until it yields, then at failure, of course, sigma x is going to be the yield strength in tension. So when we just say the yield strength, that's usually what we mean, S of y, that is the yield strength in tension. And so the principal stresses for that case, sigma 1, the maximum, will be the yield strength at failure. There's no stress in the other two directions. And so the maximum shear stress, sigma 1 minus sigma 3 divided by 2, in this case will be the yield strength divided by 2. Now let's take that result and apply it to our criterion, which says again that the maximum shear stress equals the yield strength in shear for failure. And so plugging in that value for tau max and ratioing the maximum, the strength over the stress to find the factor of safety, we find that the factor of safety is the yield strength in tension divided by 2 times the shear stress. It's a tongue twister there sometimes. So what that tells you too is that kind of an important result here is that you don't have to know the yield strength in shear to apply this criterion. And a lot of times when you go to look up the material properties, you only see the yield strength in tension, but you compare that to 2 times the shear strength for this criterion. Now what we want to do is to plot what we call the failure envelopes. So we're going to put it on axes where we have one principal stress, one of the non-zero principal stresses, and this would be for a case of plane stress, one of the non-zero principal stresses on the x-axis and the other on the y-axis. And so of course we're going to plot for all 4 quadrants. For the principal stresses both being greater than or equal to 0 is quadrant 1. If they're both less than or equal to 0, quadrant 3. And if they're mixed, then those quadrants 2 and 4. So let's start out. Oh, by the way, before we do that, if we do the things we normally do, which is that we usually say that sigma A is bigger than sigma B, then really we'd only have to plot half of this envelope. But it's traditional to show the entire failure envelope to make it a closed envelope. So in this case, we can allow sigma A and sigma B, our in-plane principal stresses, to be in either order when we make this plot. Now the maximum principal stress criterion is pretty easy to plot. It's when either one of those reaches the yield strength, or in the case if it's compression, the negative yield strength, then you have failure. So it becomes a square, and any stress state that is inside of that square, we say is safe. Now, of course, it may have, if it's right on the edge of the square, then there's no factor of safety there. But again, the prediction is we only have yielding if the stress state is outside of that square. Now for the maximum shear, again, we've set this up as sigma A on the x-axis, sigma B on the y-axis, so we want to find sigma B as a function of sigma A. And we'll start out in the first quadrant where both sigma A and sigma B are positive numbers, or could be 0, but both positive or 0. And there's two cases there. One of them, as we said, if sigma A is greater than sigma B, then our maximum shear strength turns out to be sigma A divided by 2. And so we get yielding when 2 times that value is equal to the yield strength. In other words, when sigma A is equal to the yield strength. And also staying in quadrant 1, but now saying what if we flip those around such that sigma B is bigger than sigma A, then our maximum shear strength is going to be sigma B divided by 2. And applying the same logic here, 2 times tau max being equal to the yield strength, that says sigma B is equal to the yield strength. And so our plot for the quadrant 1 looks exactly the same as it does for the maximum principal stress criterion. Okay, now let's move over to quadrant 4. So in this case, sigma A is going to be greater than or equal to sigma B. And also in quadrant 4, one of the principal stresses, in this case sigma A, is going to be positive and the other one's going to be negative. So reordering them from high to low, sigma 1 to sigma 3, we find that tau max is equal to sigma A minus sigma B divided by 2. Now, yielding occurs, again, when 2 times the shear stress is equal to the yield strength. And so the 2's cancel each other out, and so we have this equation that we can write as sigma B as a function of sigma A. Sigma B is equal to sigma A minus the yield strength. Now, you notice that's in the form of a straight line, y equals mx plus b. In this case, m would be 1, and the y-intercept b would be minus s of y. So this is what our failure envelope looks like in quadrant 4. So we get a straight line connecting the yield strength and the negative yield strength. And if we repeat that for a similar kind of analysis for this quadrants 2 and 3, then you'll see here's our failure envelope. So in quadrants 1 and 3, it looks the same as the maximum principal stress, but in quadrants 2 and 4, where the signs of our principal stresses are different, then we cut the diagonal through there instead of extending all the way out to the corners of the square like the maximum principal stress does. And there's the comparison of the two. So you can see where they vary the most is along a diagonal line that we'll talk about later represents the state of pure shear. But again, we'll get into that a little bit later when we compare these. Now, the basis of that maximum shear criterion is the observation that the movement of dislocations within the crystal structure are what causes yielding. And yielding is not caused by extension of or shrinkage in the directions, but rather by angle changes. In other words, shear deformations cause the dislocations to move. So looking at the shear strength as opposed to the principal stresses seems like a logical thing to do. And a similar kind of argument is made with the von Mises criterion. And what the von Mises criterion is based on is the observation that if we have hydrostatic stresses, so equal stresses in all 3 directions and no shear, that doesn't cause yielding. So just like if we took a block of material and put it underwater and took it to a great depth such that, again, all the stresses are the same in all 3 directions, that doesn't cause yielding. Now, furthermore, we can say that any stress state that we encounter, we can divide it up into a hydrostatic component and the rest of it. And the rest of it is called the deviatoric stress, or sometimes called the stress deviator. So here's our, and we'll do it in terms of principal stresses. Here are the principal stresses, any particular stress state. We can divide it up into a hydrostatic portion, and in this case our hydrostatic stress is going to be the average of those three normal stresses in a state of 3D, and the deviatoric then is just the difference between the two. And so this theory, the von Mises theory, says that if we look at the strain energy of that deviatoric stress, that's our predictor of yielding. Now this is where we go back to the that ugly equation that we came up with when we were looking at strain energy, and we said, for a general state of stress, there's the strain energy density, and if we integrate that over our entire structure, then we have the total strain energy. Now, if instead of using sigma x, sigma y, and sigma z and the associated shear stresses, if we use principal stresses instead, well, all the shear stresses are equal to 0. So that makes that equation not quite so ugly, and we can actually simplify it even a little bit further and say, here's the strain energy density, again, based on principal stresses. Now, this is the total amount, and so we want to divide that between the hydrostatic and the deviatoric portions of this. Now for the hydrostatic, we said the average stress is the average of sigma 1, sigma 2, and sigma 3. And so if we write the strain energy for that, again, I'm going to kind of not really spend a lot of time on the algebra here, but we end up with a strain energy density that we'll call U sub h, which is only due to the hydrostatic component. Okay, so we have the total and the hydrostatic. So to find the deviatoric portion of that, we take the total strain energy and subtract the hydrostatic strain energy. And again, that's all shown there. You can go through the algebra if you want, but we end up coming up with a not too terrible equation for the deviatoric portion of the strain energy. And now, again, we know one particular stress case that, based on a tensile test, if we only put a normal stress in the x direction, or in this case makes the principal stretch 1, that it's going to yield when it reaches the yield strength. And so in that case, the deviatoric stress would be as shown here. And now we'll compare the two. So for any stress state, we'll say that it yields when its strain energy equals that of the known case, that of the tensile test. So you can see that simplifies down, and so now we say that we get yield when this quantity, the square root, is equal to the yield strength. And that whole quantity we call the von Mises effective stress, usually given as a sigma prime. And the factor of safety is simply the yield strength divided by sigma prime. And by the way, if you're working in SolidWorks, that value, the von Mises effective stress, is what gets plotted by default. Well, that is sigma prime, and so again you can compare that directly to the yield strength to find the factor of safety. Now you can, we're usually dealing with a state of plane stress, and so in that case you can knock out one of those principal stresses, and this simplifies down to a very nice compact form for finding the von Mises effective stress. But to do this, of course, you got to find the principal stresses first. But we can bypass that as well, begin with a little bit more algebra by saying, let's write that last expression in terms of sigma x, sigma y, and tau xy. Going back to what we learned with principal stresses, and even when we were drawing the Morse circle, we have these equations for sigma a and sigma b, which if we plug those in and again do a bunch of algebra on that, end up with a pretty, an expression that again is involving sigma average and the radius. And again, do a lot more algebra on that, but we do come up with a nice, relatively simple equation here that now, without even finding the principal stresses, we can find the von Mises effective stress just from our sigma x, sigma y, tau xy stress state. Again, this is only for plane stress, but again, we can skip the step of finding the principal stresses in this case. And for a special case that we run into quite a lot, if we just have a beam that's in bending or a torsion, a tube that's under torsion and bending at the same time, well, we usually only have one normal stress in that case. We don't get into the case of binormal stresses unless we're looking at plates and shells, or then of course then go on to 3D from there. But a lot of actual stress states not only boil down to plane stress, but also to plane stress with only one normal stress. And in that case, our von Mises effective stress is really simple here. It's just sigma x squared plus 3 times tau xy squared. Take the square root of that, and that is the von Mises effective stress. So to plot the failure envelope, it's a little more complicated because of the complication of our having the square root involved here. But as we said, our prediction is the von Mises effective stress is equal to the yield strength at failure. So squaring both sides, we have the equation that's shown here. And remember, what we're trying to do is to write sigma b as a function of sigma a. So when we rearrange it like this, you'll see that we have a quadratic equation. And just applying the quadratic formula here, we come up with this expression for sigma b as a function of sigma a, and simplified down at the bottom here. Now, this is going to give us some limits right here, that we know that that square root has to be positive, and so that gives us the result that sigma a squared has to be less than or equal to 4/3 the yield strength squared. That'll give us the upper and lower limits of what the normal, the principal stress sigma a can be. And we'll work this with a numerical example here. We'll just arbitrarily make the yield strength 50,000 psi. And we're going to plot some points. The first one, let's find the absolute lower limit of sigma a. And we see that it's minus 57,000 psi. Kind of a surprise in that we're showing that the one of the principal stresses can actually have a magnitude that's greater than the yield strength. But we'll show that on the chart in just a moment. So then we go into our equation for sigma b that we came up with from the quadratic formula, and we find two roots. And so in this case, though, both the roots are identical because that square root goes to 0. And so sigma b is equal to minus 28,867 psi. So those 2 points, sigma a and sigma z, become our first point that we're going to plot. Okay, next, let's plot a couple of other points. We're going to let sigma a be minus 50,000 psi. And plugging into the formula, we find that sigma b will either be 0 or minus 50,000 psi when sigma a is minus 50,000 psi. Let sigma a be 0, and we find out that sigma b is plus or minus 50,000 psi. And we can do this with a couple more points. Let sigma a be positive 50,000, and again we find the sigma b is 50,000 or 0. And finally, look at the upper limit of sigma a, and we find that sigma b at that point is 28,867 psi. Now, if we plot those, you can see plotted 1 to 5, and again for 2, 3, and 4 there are two roots. And so of course this forms an ellipse. And so again, as we noted earlier, the von Mises criterion says that it's possible that you can have a stress that's greater than the yield strength for some particular stress states. And the other two are plotted against that as well. And you can also see the line for shear stress only. We'll show why that is in just a moment. But that diagonal where you only have a shear stress, tau xy, represents the place where the criteria are the farthest apart. Now the von Mises, if you look at actual test data, does fit the test data the best, so that's probably the best one to use. But you also notice the maximum shear isn't that much different, and it's always inside of the von Mises ellipse, which means that it's a little bit conservative, that it will predict lower factors of safety. Now, in the case of the max principal stress, again, it's fine in the quadrants 1 and 3, but for the case of shear stress, it'll actually be unconservative. It will lead you to believe that you have a higher factor of safety than you actually do. That's why we say just don't use it. You've got two choices that are much better than the maximum principal stress criterion. Now going back to the shear stress example for just a moment, again, if you just have tau xy and you draw the Mohr circle for that, then your 2 points are 0 tau xy and 0 minus tau xy, fit the circle through there, then you see that sigma A and sigma B are the same magnitude and opposite sign. Hence, it will be along that diagonal line that's shown here. So, our best fit to the data, definitely the distortion energy criterion, the von Mises. It's pretty easy to apply, certainly with a calculator or a spreadsheet. And one of the reasons, though, that the maximum shear is written into a lot of design codes is if you had to think back to when these a lot of these codes were written back when you had to use a slide rule, and coming up with the maximum shear stress was a lot easier than finding the von Mises effective stress in a lot of cases. And it's also, again, a pretty good fit, and it's conservative. Max principal stress, not only does it not fit well, it doesn't fit well the wrong way. That is, it's unconservative for some particular loading cases, and we don't recommend using that. So that's it for this time. Next class we'll look at brittle failure criteria, and we'll do a few examples.